Assalamualaikum and a very good day to everyone. I am Zuhairah and hereby will be discussing about advancement of friction stir processing on magnesium alloys. Based on previous studies, major part of the automotive and aerospace industries, also maritime, always demand for lightweight material. Recently, aluminium-based alloys have been the popular materials used in cars to reduce weight. But magnesium-based alloys have become well known for years because of their good advantages such as strength-to-weight ratio and its low density when compared to aluminium alloys. Magnesium and its alloys have recently been evaluated as excellent material as it has high specific strength, responsive castability, weldability, strong damping, and superior machinability. These are the descriptions of magnesium and its alloys. The principle of FSP applied is for the alteration of material surface after embedding a cylindrical shaped rotating tool with small probe at the tip of the tool. Then, tool was plunged into the material so that there is contact between the shoulder of the rotating tool and the material's sheet surface along the required length in the transverse direction by applying a suitable load. Heat will be generated from the contact and softens the material underneath melting temperature, while the mechanical stirring induced by the probe leads to strongly plastic deformation, resulting a dynamic recrystallized fine-grained structure. The objective of this study is to review the advancement in friction stir processing on magnesium alloys based on FSP parameters, tool properties, and its material properties. This is the flow of FSP studies done by majority research in the back time. This slide shows the significant findings in FSP parameters investigations. There were some different findings found and were described in the table below. Table 2 shows the significant findings in latest development of FSP tool. Example of material used for the tool are mild steel, stainless steel, and H13 hot working steel. Ensing and team explained that the grain size was decreased, consequently, the microhardness was improved. Increased microhardness along with before seam particles improved the wear resistance of the specimens. Microhardness was increased with the increase in particle size. Uganda described that improvement in tensile strength of the joints can be identified from the existence of well-equiaxed grains in the stirred zone. Moreover, Kayami et al. Explained that for AZ91, when transverse speed of FSP tool in higher value, the hardness profile of the cross sections of the FSP specimens increase. Furthermore, Seville et al. Explained that constant feed rate and tool's rotational speed made the grains on AZ80A became coarser in the nugget zone. Finer grains were observed at constant rotational speed while simultaneous feed rate increases. Sevian et al. Stated that the grain size was slightly decreased after single pass of FSP. Grain size reduced to 1/3 of their amount from the original condition of the AZ31B, significantly after the third pass of FSP. Besides, Kumar and team focusing on the effect of tools, rotational speed, and pin profile on micro-hardness of friction-stirred aluminium alloys. Lastly, Venkataya and team described that the width of the stirred region and the rate of material flow was observed to decrease as machine rotational speed and traverse speed were increased. Higher rotational speed and lower traverse speed came out with the higher grain density and hardness. Rotational speed affects the grain refinement level and the width of stirred zone. Traverse speed influences the material flow rate. To improve the mechanical properties of magnesium alloys, it can be concluded that by maintaining a constant tool's rotational speed and feed rate, made the grains became coarser in the nugget zone. Finer grains were found by setting up the rotational speed at constant value while feed rate increases simultaneously. The higher the traverse speed of FSP tool, the higher the hardness of the cross sections of the FSP specimens. The condition leads to better condition of profile. To be accurate, rotational speeds must be in the range of 900 to 1400 rpm so that no defects can be detected. Besides, traverse speeds must be in the range of 25 until 40 mm per minute to prevent pinholes and tunnel defect on material. Researchers believe that tool's rotational speed affects the grain refinement level and the width of stirred zone, but the material flow rate was influenced by the tool's traverse speed. Exact series magnesium alloys were mostly being applied in FSP work. These are the references related to this study. 8 references were used along this study. So this is the end of my presentation. Thank you for watching and listening.